This presentation includes two papers, and the first topic is about the first paper. The title of the first paper is Counterreactive Catalytic Effects of N-nickel versus N-nickel in Plastic Pyrolysis for Advanced Quality Jet Fuel Production. The first topic includes four parts, and the first is the introduction. The global annual output of the plastics increased year by year. In 2021, the output value reached 390.7 million tons. The combination of large-scale plastic production and low recovery rates results in significant quantities of plastic waste, which cause serious environmental pollution. The global annual output of PP is the highest among all different plastics, accounting for 19.3% of the total plastics output in 2021. PP is mainly made of hydrogen and carbon, without any oxygen, sulfur, or nitrogen, which are easier to recycle value-added products through pyrolysis, such as carbon nanotube and gasoline. If the oil produced from the pyrolysis of plastics can be used as jet fuel, it not only alleviates the energy crisis, but also effectively reduces environmental pollution caused by waste plastics. This is a Chinese standard for jet fuel. This standard specifies that the aromatic hydrocarbons content of the jet fuel shall not exceed 20%, and the olefin content shall not exceed 5%. The second part is the material and methods. The plastic used in this study was PP particles. Table 1 shows the proximity analysis and ultimate analysis of PP particles. Figure 1 shows the catalytic pyrolysis experiment system used in this study. Here's the experiment. First, placing 1 gram of PP particles into the quartz basket, and placing the quartz basket into the quartz reactor. Then putting the quartz reactor with the nitrogen flow and heating the electric furnace to 550 degrees Celsius. Then inserting the quartz reactor into the electrical furnace and connecting the quartz reactor to condensers and attaching a gas bag to the outlet of the condensers and concluding the experiment after 1 hour. Catalysts with different catalyst supports and metal loadings were prepared through wide impregnation method. These catalysts were characterized in terms of their surface morphology, crystal structure, and specific surface area, power volume by SM images, XRT, and BT methods, respectively. And part 3 is the results and the discussion. Picture shows the SM images of different catalysts. SM images indicate that the introduction of N-nickel or double dopant of N-nickel didn't lead to a significant alteration in the morphology of the catalysts. Figure 3 shows the SM images and the EDX mappings of different catalysts. EDX mappings confirm that the even dispersion of iron nickel on both supports, including the different zeolites and active carbon. Big bar shows the XRD spectra of different catalysts, which confirms the formation of iron nickel alloy in different catalyst supports. Table 2 shows the surface area and the power volume of catalysts. The doping of iron and nickel in unzeolites and active carbon led to a reduction in surface area and pore volume, mainly attributed to the pore blocking caused by the doping of iron and nickel. Figure S2 shows nitrogen absorption, desorption, atom, and process distribution of different catalysts. Figure 5 shows the results obtained from pyrolysis or PP using catalysts with different loaded catalytic metals. From the figures, we can see the double dope of iron and nickel achieved the highest liquid oil yield of 64%, and this catalyst also promotes an increase in alkene concentration by 70.64 area percent, while suppressing the yield of polyaromatic hydrocarbons and olefins, which decreased by 3.6 area and 18.7 area percent, respectively, thus facilitating the formation of aviation oil. And the double dope of iron and nickel also showed the highest concentration of carbon carbon 8 to carbon 16 hydrocarbons, reaching 96 area percent, exceeding the previous report values of 91.02 area percent. The double dope of iron nickel catalyst achieved the highest hydrogen concentration of 53.44 volume percent in the produced gas, which compared to natural gas results in a reduction of carbon emissions by 11.68%. Figure 6 shows the results obtained from the pyrolysis of PP using catalysts with different catalyst supports. The active carbon supports has no browniest and lowest acid sets, and the iron nickel doped in the active carbon catalyst achieved the highest wax yield and the lowest gas yield. When using the catalyst doped in the active carbon as a catalyst, the concentration of cycloalkenes reached up to 64.59 area percent, but the olefin content was as high as 23.74 area, and 82.98 area of the pyrolyzed oil fell within the gasoline ranges. The result, fix 7 shows the results obtained from the pyrolyzed OPP at different pyrolysis temperatures. At 450 degrees, the wax yield reached its highest value as the low temperature prevents the plastic macromolecules in the vapor from decomposing into smaller molecules, lead to more wax formation. And the highest concentration of carbon 8 to carbon 18 hydrocarbons was observed at 650 degrees Celsius. Figure 8 shows the results obtained from pyrolysis of PP at different cycle times of iron nickel supported by white zeolite. The regenerated catalyst results in an increase in olefin content, while monoaromatic hydrocarbon content decreased. The distribution range of carbon 8 to carbon 16 hydrocarbons in the liquid oil showed little variation, indicating that the number of cycles of different catalysts has had little effect on the carbon number distribution of carbon 8 to carbon 16 hydrocarbons. Overall, iron nickel catalyst pyrolysis has supported by white zeolite catalyst pyrolysis has potential for converting waste plastics into This figure shows a comparison of oil chemicals and gases products rates by using different catalytic metals. Figure 9 shows the reaction mechanisms of PP pyrolysis with or without using white zeolite, undoped white zeolite, nickel-doped white zeolite, and both iron and nickel-doped white zeolite catalysts. Without a catalyst, pyrolysis can reach up to 86 weight% wax, which contains long-chain cycloalkenes, alkenes, and alkenes. With the addition of white zeolite, the white zeolite further decomposes long-chain hydrocarbons into short-chain hydrocarbons and promotes the formation of monoaromatic hydrocarbons and polyaromatic hydrocarbons. With the dope of iron or nickel, the mass yield of monoaromatic hydrocarbons and polyaromatic hydrocarbons decreased. In contrast, the mass yield of alkene increased significantly. When both iron and nickel were introduced, the mass yield of alkene was the lowest. The iron-nickel bimatic catalyst exhibited opposite effect compared to the individual use of iron or nickel alone. The fourth part is the conclusion. The iron-nickel doped white zeolite catalyst exhibited the highest oil yield rate at 64%. The oil produced with iron nickel supported by white zeolite yielded both the highest oil yield rate and the best oil quality. The study revealed that iron nickel binary catalytic metals exhibit contrasting effects compared to the single iron or nickel catalytic metals. While iron nickel can silicic and hydrogenate alkenes to monoaromatic hydrocarbons and alkenes, which is fueled for jet fuel production. Iron and nickel predominantly decycle monoaromatic hydrocarbons and polyaromatic hydrocarbons to alkene. This discrepancy might be attributed to the fact that iron and nickel abstract hybrid ions, whereas the double dot of iron nickel doesn't. The second topic is about the second paper. The title of the second paper is Reaction Synergy of Bimetallic Catalysts on CSM5 Support in Tailoring Plastic Pyrolysis for Hydrogen and Value-Added Product Production. The second topic also includes 4 parts, and the first is the introduction. The global annual output of the plastics increased year by year. In 2021, the output value reached 390.7 million tons. A combination of large-scale plastic production and low recovery rates result in significant quantities of plastic waste, which caused serious environmental pollution. Hydrogen, which applauded as a renewable and eco-friendly energy source, is expected to play a crucial role in developing a sustainable society. The second part is about the materials and methods. The plastics used in this study include PP, PS, LDPE, and HDPE. Figure 1 shows a schematic diagram of catalytic pyrolysis system used in this study. Catalysts with different catalyst support and metal loadings were prepared through wide impregnation method, include magnetic stirring, oven drying, crushing, and calcination. These catalysts were characteristics rest in terms of their surface morphology, crystal surface, specific surface area, and pore volume. by ICM, XRD, and BET methods, respectively. The third part is about results and discussion. Figure 2 shows the ICM images of different color lists. As images discussed indicate that the introduction of an nickel or cobalt dopants didn't lead to significant alterations in the morphology of the catalyst. Figure 3 shows the XRD spectra of different catalysts. Table 2 shows the surface textural properties of catalyst supports and supported catalysts. In relation to the catalyst supports, including the active carbon and zeolites, the supported monometallic and bimetallic catalysts exhibited a relatively lower surface area and pore volume, following the occupancy of their pores by the active metal dopants. Figure 4 shows the results of catalytic PP pyrolysis of various supported nickel catalysts. Nickel doped by monazite zeolite and nickel doped in the GSM5 contributed to the two highest gas yield. It's about 61% and 60.5% respectively. The highest hydrogen composition is 49.9 volume concentration, and hydrogen yield is about 19.2 mmol per gram were acquired using the nickel GSM5 because GSM5 had intersect 10 ring micropores that could promote the cracking of the end and side chains of the PP. And nickel doped by the on the active carbon proved more suitable for jet fuel production due to its lowest concentration of the olefins and the relatively low yield of cycloolefins and alkenes. Figure 5 shows the results of baseline study and catalytic PP pyrolysis over various GS5 supported catalysts. Nickel and cobalt double dot on the GSM5 stood out from the GSM5 supported bimetallic catalyst with the highest gas yield of 64.8%. Nickel and cobalt increased the hydrogen yield to 28.7 mmol per gram compared to 19.2 mmol per gram for nickel and 10.2 mmol per gram for cobalt. This improvement could be attributed to the synergetic effect of nickel and cobalt atoms. The introduction of an nickel or cobalt onto GSM5 led to an increase in the olefin content and a decrease in aromatic content compared to GSM5 alone. Figure 6 shows the results of catalytic plastic pyrolysis of nickel cobalt doped GSM5 zeolite. Among different plastics, PP granted the highest gas yield, about 64.8%, since its numerous side chains were easier fractured, so generating more gas. PS showed the highest oil yield, 92.2% and the lowest gas yield, 7.3% due to the presence of thermal stable phenyl group, which imposed the challenge to further decompose the oil into gas. PS pyrolysis oil comprised of 52.8% benzocyclobutene, It is a valuable compound with diverse applications in semiconductor, electronic packaging, microelectronics fields. This finding result reveals that the alternative synthesis route of benzocyclobutene, which was catalytic pyrolysis of PS waste of nickel doped ZSM5. This figure shows the specific yields of individual gas from PP pyrolysis and different catalysts. This figure also shows the specific yields of oil components from PP pyrolysis and different catalysts. And figure 9 shows the production extent of the individual gas and oil components from PP pyrolysis and different catalysts. It is used for each comparison. Figure 10 shows the mechanism effects for different reaction routes of PP pyrolysis and various catalysts. Without the catalysts, high temperature induced random cleavage and fragmentation of PP chains into shorter polymer chains before subsequent decomposition to various kinds of alkyl radicals. Cyclization or dehydrogenation processes were followed to form cycloalkenes and olefins. In the molecular hydrogen transfer and aromatization processes might also occur to generate hydrogen alkenes and monoaromatic hydrocarbons. GSM5 catalyzed the aromatization and dehydrogenation of cycloalkenes, hastening the formation of monoaromatic hydrocarbons, polyaromatic hydrocarbons, and hydrogen. The cobalt-doped GSM5 catalyst removed hydrogen atoms from hydrocarbons, boosting the hydrogen production. For nickel-doped GSM5, nickel showed similar effects to cobalt on the alteration of gas and oil components, but the enhancement of dehydrogenation and the inhibition of aromatization were more profound in nickel. The nickel-cobalt binary metals improved the catalytic effects of single metals like nickel and or cobalt, specifically in the cyclization of cycloalkenes, dehydrogenation, and hydrogen transfer processes. The first part is the conclusion. From the results of catalytic PP pyrolysis of ZSM5 supported catalysts, nickel cobalt doped ZSM5 surpassed other catalysts as the optimal catalyst with the highest hydrogen yield, about 28.7 mmol per gram polypropylene, and the resulting pyrolyzed oil demonstrated potential for the use as jet fuel. The hydrogen yield of catalytic plastic pyrolysis of nickel cobalt doped ZSM5 ranged from 8.7 to 28.7 mmol per gram, whereby the highest hydrogen yield was yielded by polypropylene. Catalytic PS pyrolysis had the lowest hydrogen yield in spite of its highest hydrogen concentration, about 83.2 volume concentration. Notwithstanding its travel gas production, catalytic PS pyrolysis yielded the pyrolyzed oil with 52.8 area percent benzocyclobutene, which was promising for application in semiconductor, electronic packaging, microelectronics fields. The employment of nickel-doped ZSM5 and cobalt-doped ZSM5 could enhance hydrogen yield while reducing the cycloalkenes, cycloolefins, monoaromatic hydrocarbons, and polyaromatic aromatic hydrocarbons levels. For nickel cobalt double doped on DSM-5 catalyzed, the nickel cobalt binary metals demonstrate synergetic effects on hydrogen production by enhancing the desalinization of cycloalkenes, dehydrogenation, and hydrogen transfer process, surpassing the catalytic effects of nickel and cobalt alone. Okay, thank you for listening.